man, we're going to have a great time. Hey, there we go.
All right, brilliant. In that case, Belinda, good luck.
Thank you. All right, thank you very much. It's a pleasure to be here and a pleasure to be in front of you all in person and online. It's been a really great workshop and it's been a really exciting room to be in. So I'm going to be speaking today about some of the work I've been doing over the last couple of years since moving to Oxford. My PhD background was in Doppler imaging and Zeeman Doppler imaging, so very different to what I'm doing now. And I've been working on this in between madly following up test planets with radial velocities. So it's been a good project to sort of have running in the background because you can just set the runs going on the supercomputer. So the goal of this project was to look at the hyperparameters from a Gaussian process fit and see what relation they had to stellar parameters. And the reason why we're sort of interested in this is, of course, our stars are not uniform, lovely, beautiful, simple sources of light. They have features on their surface, and those features have some impact on their light curves or the radial velocity time series. And so I thought I'd put this one up again. Oscar showed it earlier in the week. It's a beautiful image of the sun and the radial velocities of the sun, and you can see how the solar spot features impact on the radial velocities we get. So in theory, if we're fitting a Gaussian process to our data and we're getting some sort of information from that, then that should we should be able to pull some sort of information about physical processes on the star from that.
Linda, I'm sorry, but I do believe that we do have technical issues because it doesn't seem to update.
It's okay. I haven't hit go yet.
All right.
No.
Is your presentation online, or is it only on
On my computer.
what? Keynote about? There's anyone who's got EduRoom and a Mac, and we could transfer your presentation.
I'm currently connected on EduRoom.
Okay, that's odd.
I'm gonna try transferring.
No, it's not with it. I think it's not going to make a big difference.
You see, this is why it's up your clock.
Okay, I see. Yeah, it's. Come on. Come on.
I'm sorry about this. It was wonderful.
I'll have to.
No, it doesn't. It doesn't like me. I can. One thing I could do is if I go. There we go. So I've stopped sharing. I share again.
It's a classic.
No. Oh, it's doing something. Hey, okay. So at least let's split this way. No, okay. This is gonna be. I'm gonna have to like reshare and share again every time. I could try doing it through interpretive dance. Sharing. It is still sharing. Okay.
All right. Great. We're back.
Hey. Okay. So we lose the animations, but that's okay. There's gonna be some punchlines that just happen. So, yeah, there's gonna be no comedy value. That's sad. All right, so where were we? We were talking about how stars are terrible in that they're not uniform, but that's okay because we can do physics by understanding how they're not uniform. So the starting point of this project, okay, so we're going to be fitting Gaussian processes to stellar models. So stellar models where we know the stellar rotation period, the spot number, the spot decay time, and the spot distribution and spot area. So from this, we have a fairly basic stellar model with linear limb darkening and distribution. So we've got 100 of these models with 250-day durations, sampled at 2 points per day. so 500 points in total in each light curve. And we get both flux and radial velocity. So we simulate radial velocities as well from the same spot configuration. So this is just an example of some of the stellar models that we have. So we have a nice sort of longer rotation period one here, and a shorter rotation period one, slightly different spot distributions and spot numbers, and different spot decay time. So you end up with different looking light curves and radial velocities. So I was looking at that. I'm going to close this so I'm not confused. So the GP kernels that I'm looking at for this, I'm going to our old favorites, the quasi-periodic kernel. So this is our squared exponential and sine squared kernel. It's an oldie but a goodie. It's been used for in a whole number of different papers looking at studying stellar data with GPs. I also look at the QP cosine kernel. So this was introduced in RADIAL 2021. So it includes a cosine component into the QP GP. And I've also been investigating the celerity rotation kernel, but I'm not going to present those results today because after discussions with Dan over the last few days, I can't trust the results that I've got. So it's going to take a little bit more time for me to actually really get to the bottom of that and really understand what's happening with that kernel. So, to solve these GPs, I use the George package to construct my quasi-periodic kernel and my quasi-periodic cosine kernel. I include a jitter term, so these model light curves aren't perfect samples from a GP. There's going to be some deviation of the light curve from a perfect GP. So this jitter term sort of helps to absorb some of that. I run an MCMC to sample my posteriors, and I use nice broad uniform prior distributions on all hyperparameters purely because I don't want to bias anything. So to start off with, I look at the quasi-periodic kernel. So this is a reminder of what it looks like and what its covariance function looks like as you change some of these hyperparameters. In particular, I'm showing the behavior with the L term. So this is our length scale, our evolution scale, and we have our gamma term, which is the harmonic complexity. And this sort of shows, you've got an example here. On the far left, one rotation period later, you're back up to being closely correlated, but because of that squared exponential envelope, you're not going to be perfectly correlated as you were one period before. And then you can change the degree of correlation, the periodicity with controlling that L term, and then this gamma term dictates how much that correlation drops off between single periods. So it's just to give you a bit of a feel. What do we think that these actually correlate with? So we have our amplitude here, which relates to the variance of our data. The period relates to the stellar rotation period. We think the stellar evolution timescale has some correlation with the spot evolution timescale. Harmonic complexity, who knows? We're not sure.
You matched the shirt on purpose.
Maybe. So I know we don't really like correlation coefficients, but this does sort of explain. So this is the results from comparing the input stellar model parameters of, I've got period, spot evolution timescale, the number of spots, and the average spot distribution. And then we have our output quasi-periodic hyperparameters of period, that L scale, that L that controls the squared exponential decay, and the gamma, which is our harmonic complexity. So as we hoped, we have this beautiful correlation between period and period. So the stellar rotation period correlates very nicely with the period of our QPGP as we hoped. going along that diagonal, we have a nice strong correlation between the evolution timescale of, evolution timescale of our squared exponential, and then our spot evolution timescale tau. And then as for gamma, you have some correlations here, but not really as strong as anything else in our sample. So plotting these up, again, you can see this beautiful one-to-one correlation, and then I've shown the residuals here just to highlight how at shorter periods, we're doing less well than at longer periods, but this is purely because this is where we come into sampling. We've got finite sampling, we use the same sampling across all of our light curves, no matter the period. So if you're a short period with the same time sampling as a long period, you're going to do less well.
Did you tie in your simulations, did you tie your spot lifetime to the rotation period, or are they completely simulated separately? Separately.
Yes. So the way that we generated the grid of spot evolution times is we went sort of a factor of 1 to 10 times the rotation period.
Good, which explains why you had a high correlation in the previous.
Yes, yeah, exactly. Looking at the GP output squared exponential length scale and our model spot evolution time scale, we get a beautiful correlation, which behaves slightly differently as you get sort of further out in the data. So this purple line here with the T next to it, that's the total time span of our data. So we have some models that have spot evolution time, so taus, that are longer than our data set. And sure enough, like it doesn't do so well past there, which you don't really expect it to. But interestingly, it doesn't do well, but it then overestimates what it thinks the spot evolution time is. You get some sort of underestimation in this sort of less than half a period. Half the time span. It tends to preferentially go under overestimate. Overestimate, underestimate. It always confuses me up or down. Anyway, you don't do as well. So looking at the harmonic complexity, we do see some correlation with stellar rotation period. Again, I think this comes down to sampling, because the harmonic complexity is, how many bumps and wiggles you get within one period. If you have really long period data, then you've got more of a chance to get those bumps and wiggles into one period than if you've got shorter periods within the same time sampling. And then in terms of the correlation of the harmonic complexity to the spot evolution time, if I go back to, that one, you can see that sort of period and tau have a similar sort of level of correlation. But if we remove the period from it, so if we look at the ratio of the spot evolution time to the period, then we see that there's no correlation at all. Right, next to the cosine kernel. Now this one was introduced to cope with scenarios where you have, symmetric spots around a star where you get this sort of signal in your light curve at half the period. So particular spot distributions can induce this sort of secondary, if you plot their autocorrelation function, you get a secondary peak at half the period. So this was introduced as a way of being able to cope with this. And you can see that as, this is the same example that I started with before, as you increase this fractional term on your cosine component, you increase this sort of bump in the middle of your at half the period. So again, what do we expect this to relate to? So we've still got our stellar rotation period here. We hope that, in circumstances where you get that signal at half the period, this would cope better at pulling out the period. You've still got your spot evolution timescale in that section. Again, harmonic complexity and the fraction, whether or not that correlates to anything in our stellar model is unsure. So again, this is our grid of correlation coefficients. Again, very happy to see that period and period correlate. It's exactly what we wanted. We've still got our correlation between the tau and the L. The fractional component doesn't really seem to be doing much. And we're getting a very similar looking correlation grid to what we had for just the straight QP one. And in fact, if I plot the plots, you'd think that I was showing exactly the same plots as before, but I'm not, I promise. These aren't actually different. I had to like flick between them to make sure that I was plotting the right ones, and I was. And again, same with the harmonic complexity. And the reason why is that for my stellar models, despite a lot of them having about 50, a fairly substantial fraction of them show a secondary peak in their autocorrelation functions at half the stellar rotation period, despite that being a feature of the model curves that I have. The QP cosine GP was still preferentially pushing this fraction value to 0, to very small. So it was happily just pushing all of the information into the main cosine, QP component. Yeah.
Just it's a stupid question, but gamma cannot do that basically.
Like
this, fit this second peak.
Yeah.
Because basically, you increase the gamma or decrease it. I don't know in which direction it goes, but basically, you can increase the number of ups and downs. No.
Yeah. I guess because there's no period. I don't know. Gamma doesn't really think about periodicity. I think you would still perhaps get some circumstances where, because it's looking for periodic structure, that the period P term, the periodicity in the sine term might try and fit to that one, and then it might mistake that as the true period. And so the cosine component explicitly forces it not to do that. But you're right, it looks like exactly as you're saying, that it actually really doesn't care if it's that. That, at least that's the impression that I'm getting by the fact that it seems to just want to push that fractional term to 0. What do we know? Where are we at now? So we recover well stellar rotation periods and spot decay information from a quasi-periodic GP, which is nice. It's what we hoped it would be. We get not really much of a correlation with stellar characteristics in the harmonic complexity. I would like to investigate further different spot distribution patterns. So one thing that we didn't do, we just left them sort of uniform, but changing their area or the number of spots. But it'd be interesting to investigate different ways of distributing spots on the surface to see if that changed this sort of complexity behavior. So now on to radial velocities, because this is the important, exciting part of this conference. And I just sort of put this up there as this very unscientific histogram of occurrence rates of the phrase Gaussian processes and radial velocity in the abstracted ADS papers. And you can see they've become really popular. They've really shot up in popularity. So, and I feel like 2022 is going to be yet again up there. So it's important to, I don't know, it's the timeliness of really studying how GPs and radial velocities work together. So the next step in my analysis was to take, so I've done this GP fit to our model light curves, and now doing exactly the same fit to the model radial velocities and compare the hyperparameters that I get between each. So this is what this plot is showing. I have the light curves on this axis and on the vertical axis, and radial velocities on the horizontal axis. And with the period, we get a really lovely one-to-one correlation. I believe that one outlier is the same outlier in the other flux plots. So the radial velocity one was able to fit it beautifully, and it wasn't an outlier and just radial velocity alone. But for some reason in the flux, it just didn't want to fit. I tried. And yeah, you get some scatter in your radial velocities, more scatter at shorter time scales. same behavior as we saw before. Again, with then the evolution time scale, so this is the L parameter in the QPGP for radial velocities and light curves, a beautiful correlation there, and then that purple dashed line is the extent of the data. So past that line, there are still some models that are out there and they fit far less well. There's no sort of global trend though, it's just scatter at that point. Now this is I guess one of the big takeaway plots from this, and this is how well the harmonic complexity from your light curve matches the harmonic complexity of your radial velocities, and the answer is it doesn't. You get a systematically higher harmonic complexity in your radial velocity data than you do in your light curves. So if you're training your GP for your radial velocities on a light curve, be aware that you're going to have to, while you can use your period and you can use the evolution time scale, be wary that the harmonic complexity is likely going to be higher. So yes, that's the big underlying statement of that section of work, is that you can use the rotation period, you can use the evolution length scale, but be very careful with the harmonic complexities. So future steps. One thing I want to explore further, I've done some tests on, so the radial velocities that I showed are ideal, perfect radial velocities. Let's put an RV machine out in space and get the same sampling as we do for space-based photometry. I've done some tests degrading that sampling, and as you expect, the more you degrade your sampling, the worse your fit to the hyperparameters and the less well they correlate. But that's still a really ideal case, and so the other thing I want to explore is, we have larger uncertainties on our radial velocities as well, so how does that impact our ability to compare hyperparameters from photometry and hyperparameters from radial velocities? Other thing, as I mentioned before, increasing the complexity of the stellar model. We've just used a fairly uniform distribution of spots. What happens when we go, okay, a polar spot, or we have the butterfly diagram pattern that we have on the sun? How does that change the way that the different hyperparameters fit? And also looking at more kernels. So I mentioned the celerite one. That's certainly one that I'm looking at. I've been hearing, there's the starry process. It's just that one. There's so many kernels out there, and then combining those ones with other sort of decay timescale ones, putting multiple kernels together. How many different ways can we try and probe this, and how many different sort of aspects of a star can we investigate? So yeah, and then that comes in with, okay, let's increase the complexity of our stellar model so that we can model these things and then see what effect they have on the hyperparameters of GPs. And yeah, it's GPs all the way down. And let's see what happens. So open up to questions, suggestions, criticisms.
Well, first of all, let's thank Belinda for an excellent. Just as a side comment, I think the technical difficulties highlighted how difficult it is to deal with activity, but we managed to fix it, so hopefully we can fix it in the future. Future looks promising, right? Any questions? In the back, let's start there.
That's you.
Yeah. Okay. Seeing that the quasi-periodic cosine, it's for the most part the same as the quasi-periodic, but for the same term for the harmonic complexity, it will be allowed to have more harmonic complexity once you fix that term because of the cosine component, right? Like if you fix the gamma parameter in the quasi-periodic cosine,
yeah,
it will have more harmonic complexity. It might have more because of the cosine component. So would it be like a reasonable thing to do to train in a QP in photometry, get that gamma parameter, and then apply a quasi-periodic cosine in radial velocity. And usually the gamma parameter is more difficult to fit than just a scale on something like that. Do you think it could work better, or will be just useless, like a waste of time?
So let me see if I'm understanding. So you train your, you define a QP, purely quasi-periodic GP on a light curve.
Yeah.
And then you take those hyperparameters and then use a quasi-periodic cosine to do your radial velocities.
Yeah, you're still fitting basically two new parameters. In the other way would be gamma and amplitude. This time it's two amplitudes.
So I think you're suggesting like the harmonic complexity of the light curve is a lower bound of the harmonic complexity.
Yes.
So you just add an extra term and fit for that term.
Yes. Yeah, I don't know if actually will help or will be just exactly the same, doing.
Yeah.
Scenario.
It probably depends, because I think the caution with the cosine is that the cosine one is only meaningful when you have signals at half the period. So if you're not seeing a half a period signal in your radial, I think that's.
So, I mean, one thing about the simulations we did, which is not necessarily very physically realistic, or at least we made no attempt to approximate anything but a uniform distribution of spots on the stellar surface, right? So there's no active longitudes, there's no active latitudes, so that is not very physically realistic. The quasi-periodic cosine may come into its own more when you have these phenomena, which we didn't include in these.
All right, Xavier?
Yes.
Did you included only photometric effect in the velocities, or also like convective blue shift?
I don't think we actually did in this case.
No, I think it was just the photometric.
It could easily be done.
So,
Yeah.
use like soap or whatever.
Or we can do it. This has an approximation to it, which is reasonable. It's just then you have to decide what the convective blue shift suppression is.
And then can you do exactly the same thing on the sun, on the solar data?
Yeah.
Because you should be. And you have all the information about number of spots, about the periodicity, and so it would be nice to see how it behaves in the case of real data.
Yeah, I think actually with the note that I've written down here on my slide, I think we do include it's a delta RV from rotation and delta RV from convection. So that note
I think
tells me
that's
probably
what the code does, but then I think by default the delta V for convection is 0.
okay.
So it depends if we modified it or not.
Okay, I can't remember that.
Related to the difference between the quasi-periodic and the QPC, did you compare the goodness of fit of both of them?
Not in any rigorous, strict way, no. But in a mathematical way.
Generally speaking, you can get what visually looks like extremely good fits to basically all the
Just wondering if one was systematically better fitting than the other.
We should check.
Well, let's go with Nathan and then Baptiste.
It's online. No. So, my question is there any reason to actually have an harmonic complexity parameter? What I mean is, it doesn't seem obvious to me that it has a meaning as a parameter. And it seems like it's something that we do because people do it, but
it's something that we do. I think my interpretation of it is what's the if you're thinking in terms of starry, it's what's the degree? What's the smallest degree that you need to represent the surface in terms of what you can see in the data?
The degree of
spherical harmonics. What's the resolution? It controls, as Belinda said, it controls the number of bumps and wiggles per period. Right.
It controls the how peaked are the iterations.
It's more than that, because sometimes you can have multiple inflections per period.
Okay.
And we see that in real light curves. That was in Oscar's talk on Monday, in real RV curves and light curves. So, I mean, you couldn't do it just with sine squared or pure cosine term.
Yeah, we can talk about it.
It's an online question from Luca Malavolta. Changed. Very interesting work, Belinda. Regarding the harmonic complexity being different in the light curve and the RV curve, all other parameters are going to be influenced if you fix the harmonic complexity of the RV to the light curve value. Or to the priors of Lopez Morales et al. 2016 or to Peter 2021.
So what would happen if you were to use your light curve?
If you were to fix your harmonic complexity to the value, for example, of the light curve, all the other parameters are going to be influenced by this.
That's a good question. I'd naively just say that you just wouldn't get as good a fit as you would if you had a higher harmonic complexity. You're just not going to do as well at removing the signal that's covering. Maybe
Sine was actually
you've got a jitter term, maybe the jitter term would absorb it, so you might not see it as much, but you're
yeah. If you could,
yeah,
you cannot lose.
wouldn't get the same
Actually, that's thing.
fit.
They just changed one.
Brilliant. Let's thank our speakers and let's go for coffee.